Hello, everybody. It's a great privilege and a pleasure to be here, to be giving a talk in front of this audience. I want to say thank you for the hosting Ant Group and for all the organizers who did so much work to bring us all together today. Thank you for all this work, and thank you everybody for coming. This is exciting. Today I'll be talking about the new set of libraries we are building to complement Velox. We'll be talking about what's Axiom and why we decided to start building it and how it should expand Velox into the front end of compute. There are many database query engines, many database systems. They support different use cases, have different characteristics, but they all share roughly the same high-level architecture. You can find in any query engine a parser, or like SQL parser, or Spark HQL parser, or some sort of Python data frame API. And there is an analyzer which converts a SQL tree or Python data frame into a typed semantic tree, figures out the types, figures out the names, lookups some metadata. There is usually an optimizer that takes a logical plan and figures out what's the best, most efficient way to execute that plan to produce the desired data. And those optimizers often collaborate with the storage connectors to figure out if maybe some operations like filters, aggregations, sometimes even joins can be pushed down into the storage nodes to further optimize the query performance. There is also a runtime which takes care of coordinating execution among possibly multiple nodes on the cluster, figures out how to split the input data into chunks that are small enough that they can be processed by a single node, how to distribute those splits across all the workers available in the cluster, how to manage workers producing results, aggregate them, configure shuffles, and so on. And there is a execution, like a single node execution, a component responsible for receiving a single node fragment of the overall query plan and producing results just for that fragment by processing a subset of the splits of the query. The execution component is what we were focusing when we were developing Velox. We noticed that every query engine requires an execution component, and while they are different among different engines, there's a lot of similarities. Many of them need some sort of a hash table. They need an aggregation operator, a join operator, different kinds of join operators. There's a lot of commonalities that we thought it would be valuable to build a library of building blocks which could be extended and modified for any particular engine and still kind of share the common core. And so that's what we've been doing with Velox, and I would say we largely succeeded. Presto adopted Velox, Spark, Gluten, various streaming solutions Pedro was talking about, like AI data training, now leveraging Velox, and we keep seeing more and more systems using Velox as a building block to accelerate development, to bring more efficiency. And so now we are noticing that there's a bit of hurdle between the front ends of all those query engines and the mostly unified backends through Velox. We're seeing that There is a disconnect with the language being used to build those systems, like Velox-based workers are running it mostly in C++, but front ends are still primarily using Java or Scala, and there is a bit of a challenge to how to get those two systems communicate smoothly. We often see GNI solutions which introduce a lot of challenges. There is a bit of disconnect, and developers have to think both in Java land and in the C++ land, which is a bit challenging. And so we're looking at that state of where we are, and so we're seeing that there are a lot of opportunities in optimizing the front end and unifying that front end through building blocks, similarly how we have unified the back end, the execution. So for Presto, we're seeing that when we're trying to put together a single node solution rather than a big cluster, but just a single node which contains both the coordinator logic, the front end, and execution, we have to have two separate processes. The Java process that runs the optimizer, the parser, the runtime that manages the execution, and a separate native C++ process that does the heavy lifting of data processing. And that means that we need to communicate those two processes, which is redundant, inefficient, and it would be much more streamlined if we could run a single native process that takes care of the whole query execution. We also seen wrinkles where the optimizer needs to collaborate with the execution, for example, for constant folding. If you have an expression in the query that doesn't depend on anything and can be evaluated on without reading any data, we want to do that so we can maybe then optimize the query further. And currently, for example, in Presto, we rely on having Java implementation of all the functions and having those implementations match exactly the implementations in Velox. And that's a bit of a wrinkle as we move forward, new functions being introduced, and it's kind of unfortunate that you need to implement them twice, once in Java, once in C++. For Spark, we also noticing that having a need to run Java executor, which is capable of speaking Scala-specific, Java-specific protocol with the driver, and a sidecar C++ process that runs the query fragment, it means we need to allocate extra memory, extra CPU cycles. For example, we noticed that just to stand up a very thin Java executor, we need to give it 3 GB of memory, which is a bit large for almost getting very simple functionality, just a pass-through from the driver, the request from the driver to the sidecar process, and maybe some metrics flowing back from the sidecar process to the driver. We also believe there is quite a bit of complexity and operational overhead associated with using of GNI. It's not very easy technology to work with. So we're thinking it would be nice to find a way to build an all-native solution. And so what we are also seeing that for the AI data training, we currently have an optimizer that's lacking a bit of power, it's not as powerful as Spark optimizer, as Presto optimizer, but at the same time it has some AI-specific functionality which is missing in those other systems. And so we really feel like we need a more powerful, more extensible optimizer written in C++ that can be used in many systems and customized as needed. We also seen this inefficient communication between Java-based or Scala-based front-end and native C++-based execution, which we'd like to optimize. We want to improve the DevX experience, just allow the community to move faster and not have to constantly switch between thinking in Scala or Java and thinking in C++. Those languages are quite different. The way you write code in those is pretty different. You need like a different mindset. I personally find it very difficult to switch back and forth the two. And so those are kind of challenges, but also maybe those are opportunities. And so when we're thinking about opportunities, this is an opportunity to build something new and to make things even better. And we're very happy about how like Velox idea of building a library with extensions and allow other engines to leverage it to rebuild the execution component. We want to take it to the next step and build a set of libraries which allow someone to rebuild the front end of the query engine. And we want to follow the same principles as Velox does, that it's a set of components. You can use some of them, you can use all of them, you can pick and choose what you use, you can customize each of them, you can adjust. It gives you freedom, it doesn't constrain you too much. And so the components we are looking at to build as part of this, under this umbrella of a new project called Axiom, the SQL parser, the optimizer, the runtime, and of course we would need to extend the connector APIs that were initially introduced in Velox to include functions that support metadata lookup during analysis of the query, the split generation, and APIs, for example, to create tables, to roll back, like in case of a table write failure. So that's a new project. You can find it on GitHub under name Axiom. All those kind of components, they are meant to be compatible with Velox-based execution. So you should be able to leverage those if you use Velox for execution already. Just to kind of, like, this is all very new projects, so we're kind of just starting. We believe this is the right direction going forward, but we haven't yet fully built out the libraries. Just to give a sense of what's kind of already available, if you're curious to give it a try, just to see what it feels like to kind of have this composable front end. We include a simple SQL CLI with the repo. And so that CLI, when you start it, it has by default configuration with the TPCH connector, so you can query TPCH tables. You can do like simple queries, like with aggregations, with joins. You can do like statements like describe or show columns just to kind of see what the schema of the tables are. And you can also run explain commands on the queries if you're curious about what kind of query plan is being generated by the optimizer. We'll hopefully get a chance to talk about it a little bit more. There are multiple flavors of the explain commands. There are like explain type, and then there are like 4 different flavors where you can ask to show a logical plan, essentially the equivalent of SQL, what gets produced by the parser. And then you can show the graph, which is an internal representation of the query inside of the optimizer. You can ask it to show the physical optimized plan and also show the final Velox multi-fragment plan, all with this explain command. To kind of just put this all together, so this is how we like seeing, like if you decide to use all of the Axiom components, this is what it would look like. You would either have like a SQL parser or a data source, some sort of a data frame API, maybe PySpark, maybe something else. And they both produce a logical plan. Logical plan is a new set of plan nodes introduced by Axiom to represent the query. The logical plan becomes the input to the optimizer, which produces a Velox multi-fragment plan. And you can configure the optimizer. You can ask it either to produce a single node plan, single node multi-threaded, or single node single-threaded, or multi-node distributed plan where you would see multiple fragments. I'd like to just kind of give you a little bit like a kind of, detail about like how we are putting this together. Just essentially to kind of give a little bit of a sneak peek, just pique your interest in the project. We wanted to have support for PrestoSQL in the new front end, so we put together a PrestoSQL parser, took the grammar file from original Presto project and generate the parser using Antler, and then essentially use the new plan builder, a different one from which exists in Velox code base. This one is producing a purely logical plan. It takes care of resolving the names, like table names, column names, resolving the types. It supports type conversion, like implicit casts from the input types to the types required by a particular function. And it allows one to parse the query and resolve all the types to produce a logical plan. This new plan builder can also be used standalone, and we hope to add Python bindings to it so that you can have a Python data frame API, which would result in producing the logical plan that can go into the optimizer. The explain command I've mentioned before, like if you use a type logical, it would show the logical plan produced by the plan builder. There is a difference between logical and physical plans, and you would notice if you look at the logical plan nodes available in Axiom, there are a lot fewer nodes in logical plan than in the physical plan. One of the most obvious differences is that there is only one join node in the logical space. But in Velox, there are multiple join nodes. There is a hash join, merge, index lookup, like cross join, which is like nested loop. There are spatial joins. That's simply because in the logical space, we express the intent. We express that we just want to join two data sets, and we specify how exactly we want to join it, whether we want to have all the rows that may have matches on both sides for inner join, whether we want like all the rows from one side and maybe nulls for the right side if they're missing for left and right joins, or like a full join. And in the physical space, there's a lot more configuration of specific joins because they specify exactly how we want to execute that join. Do we want to build a hash table? From which side of the join? Do we want instead to use a merge join because somehow the optimizer was able to figure out that both sides of the join are already sorted? Another difference between the logical and physical plan comes like when we have an order by or limit. In Velox, we also have a special plan node top n, which combines order by with limit because it's more efficient to execute order by with limit as a top n, where you don't sort the whole row, you just keep a set of top n rows at any given time. It helps with memory management, helps with CPU time. But in the logical space, we don't have top n. That's optimization in the physical space. That's what optimizer could decide to use to implement order by plus limit. And so here we are also kind of just showing that like if we type explain, type logical, we'll see sort plus limit. But if we type explain, which by default shows the final plan, the executable Velox plan, it will show the top n node. The subqueries also exist primarily in the logical space. like if in a query, if you have a subquery, typically you don't see the subquery in the final executable plan because it gets converted into either semi-join, anti-join, semi-join filter, or project, depending on whether the subquery is using in a filter or in a project node. It can be scalar subqueries that are not correlated, that can be executed standalone or converted to nested loop joins. And so that's just the difference between the reason why we need to have a separate logical plan nodes defined in Axiom and cannot just reuse the plan nodes from Velox. So that was about the parser, which produces the logical plan, and then we need an optimizer that figures out how to execute that logical plan in most efficient way. And so we really are aiming to build a powerful, extensible, cost-based optimizer that can be used in multiple systems. We want to have first support for subfields, like keys in the map or fields in the struct, which is critical for optimizing queries that's used in AI data training, queries which run on very wide data sets with huge maps, very large arrays, large structs. If you're curious about where we are, how far along we are, we have the TPCH plans produced by the current optimizer available on GitHub. So in the optimizer today, we decided to not build the optimizer as a rule-based, but rather build it graph-based. And essentially, the optimizer is composed of 3 stages. We take the logical plan, convert it into a query graph, which is created of derived tables. And at this point, we are doing the tracking of the dependencies, push downs, and simple optimizations which don't require comparing the costs of the plan to decide whether optimization is good or not. Essentially, heuristic-based optimizations primarily go into this first 2 graph stage. And then there is this plan enumeration phase where we are building the physical plan from ground up by adding 1 table and then another and costing the plan as we go and saving partial plans into memo and figuring out which way to go, which sub-plans are promising to continue building upon, which needs to be discarded early, and finally arrive at the optimal physical plans, which simply gets translated to Velox multi-fragment plan. I think that's what I have today. Again, thank you everybody for coming. I'm happy to answer questions if you have them. So do let me know.